Given f of x equals this rational function, we want to find f prime of x, the derivative function, and f prime of 4 using logarithmic differentiation. So for the first step, we're going to substitute y for f of x and rewrite the function as y equals the rational function. Now the next step in log differentiation is to take the natural log of both sides of the equation. So we'll have natural log y equals natural log of this fraction. Now we want to expand the right side of this equation as much as possible using the properties of logarithms, which are given here. Well, the first thing we should notice is that we have a fraction here, or division, which means you can write this as a difference of two logs, but then also in the numerator we have a product here, so I can write these two as a sum of two logs. So we would have natural log y equals natural log x squared plus natural log of the quantity x plus 2 to the fourth, and then because of the division we have minus natural log of the quantity 2x squared minus 1 to the third. And now we can apply the power property of logarithms, which means we can take the exponent and move it to the front of the natural log so that we have a product of the exponent and the natural log here, here, and here. So we'd have natural log y equals 2 natural log x plus 4 natural log of the quantity x plus 2 minus 3 natural log of the quantity 2x squared minus 1. Now for the next step, we'll differentiate both sides of the equation with respect to x. When we differentiate natural log y with respect to x, we'll have to perform implicit differentiation, which means we'll have an extra factor of dy dx because the expression is in terms of y, not x. So our derivative here would be 1 over y times dy dx. Now on the right side, to find the derivative of the natural log functions, we'll use this derivative formula here. Notice how it includes the chain rule, where u is the inner function. So the derivative of 2 natural log x is equal to 2 times the derivative of natural log x, which is just 1 over x. Notice in this case, the inner function u would be equal to x, and u prime is equal to 1, so we don't need the chain rule, plus 4 times the derivative of natural log of the quantity x plus 2, that'd be 1 over u, or 1 over x plus 2, times u prime, but again the derivative of x plus 2 is equal to 1, minus 3 times the derivative of natural log of the quantity 2x squared minus 1, which should be 1 over u times u prime, or 1 over the quantity 2x squared minus 1, times the derivative of 2x squared minus 1, which is equal to 4x. Now let's go ahead and find these products here. We'd have 1 over y dy dx is equal to, this would be 2 over x plus 4 over the quantity x plus 2. Here we'd have minus 12x divided by the quantity 2x squared minus 1. And now to solve this for dy dx, we would multiply both sides of the equation by y. So we'd have dy dx equals y times this sum and difference, so 2 over x plus 4 over x plus 2 minus 12x over 2x squared minus 1. So this is our derivative function in terms of x and y, but since we know y is equal to the function, we can perform a substitution for y so that we can write our derivative in terms of x. And again, we're going to substitute this fraction here for y on the next slide. So again, what we've done here is substituted the entire function here for y. And now the rest of this problem is going to be algebra. So for our next step, we're going to go ahead and distribute here. Notice when we multiply by 2 over x, one factor of x here is going to simplify with this x here. So we would have 2 times 1 factor of x times 4 factors of x plus 2 divided by 3 factors of 2x squared minus 1. And then for the next product, notice how 1 factor of x plus 2 is going to simplify out. So we'd have plus 4 times x squared times Again, one factor of x plus 2 will simplify out, so we'll have 3 factors of x plus 2, and then we still have 3 factors of 2x squared minus 1. And for this last product, nothing simplifies out, so we'd have minus 12x to the third, 4 factors of x plus 2, and now we have 4 factors of 2x squared minus 1 in the denominator. Now if we want to try to combine these three fractions, notice how this would be our common denominator, and notice how these two fractions are missing one factor of 2x squared minus 1 in the denominator. So as long as we multiply these two fractions by 2x squared minus 1 over 2x squared minus 1, we would have a common denominator, which means we can write dy dx as one big fraction with a common denominator of 2x squared minus 1 to the fourth, but the numerator of this first fraction would now be 2x times 4 factors of x plus 2 and 1 factor of 2x squared minus 1 to obtain the common denominator. And the same thing for the second fraction. We'd have 4x squared times 3 factors of x plus 2 and 1 factor of 2x squared minus 1. And then for this third fraction, it already has the common denominator, so we would just have minus 12x to the third times 4 factors of x plus 2. Now looking at the numerator, we're going to factor out the greatest common factor from the three products. Again, looking at the three products in the numerator, the greatest common factor would contain a factor of 2, 1 factor of x, looks like 3 factors of x plus 2. And then since this product here does not contain a factor of 2x squared minus 1, this would be our greatest common factor of the numerator. So now we'll go and see what's left after we factor this out of each of these three products. Well, if we factor this out of this first product, the 2 and the x are factored out, and so are 3 factors of x plus 2. So we're left with 1 factor of x plus 2 and 1 factor of 2x squared minus 1. From the second product here, we'd be left with a factor of 2x. We're factoring out all of the factors of x plus 2, but we still have a factor of 2x squared minus 1. And then for this third product, we factor out 2x from 12x to the third. We'd have 6x squared, and we still have 1 factor of x plus 2. And now finally for the last step, we're going to simplify inside these brackets by finding this product, and this product, and then combining like terms. And we'll go ahead and do that on the next slide. So we'll have 4 products here. X times 2x squared would be 2x to the third. Then we have minus x plus 4x squared minus 2. Then here we'd have plus 4x cubed minus 2x. Here we're distributing negative 6x squared, so we'll have minus 6x to the third minus 12x squared. And now again, for our last step, we'll go ahead and combine the like terms inside these brackets. So we have 2x to the third plus 4x to the third minus 6x to the third. That would be 0. Looking at the x squared terms, we have 4x squared minus 12x squared. That would be negative 8x squared. Looking at the x terms, we have negative x or negative 1x minus 2x. That's minus 3x. And then we have minus 2. So this would be our derivative function. If we wanted to, we could factor a negative 1 out of this to make these terms positive. Let's go ahead and do that. We'd have dy dx equals, again, if we factor negative 1 out, we would have negative 2x times the quantity x plus 2 to the third times, factoring the negative out changes the sign of each of these terms here. So we have 8x squared plus 3x plus 2 all over the quantity 2x squared minus 1 to the fourth. Now remember, they also asked us to find f prime of 4, which means we'd have to substitute 4 for x. I've already determined this value using a calculator. It comes out to approximately negative 0.2657, which means this would be the approximate slope of the tangent line of the graph of f of x at the point when x equals positive 4. So again, here's f prime of x, or dy dx, and here's f prime of 4. Let's go ahead and verify this graphically by taking a look at the slope of the tangent line at x equals 4. Well, here's the graph of our function. Here's the point on the function when x equals positive 4. If we sketch a tangent line at that point, it would look something like this. And since f prime of 4 was approximately equal to negative 0.2657, that means the slope of this tangent line would also be approximately negative 0.2657. And this does look correct for the slope of our tangent line, verifying that our work is correct. Okay, I hope you found this example helpful.